Welcome to week number 10 of ECE 111, Introduction to ECE. This week, we're going to look at using Matlab to solve problems you're going to encounter when you take ECE 311, Circuits 2. Now, if you look at the curriculum for our ECE program, this would be for computer engineering. It's similar for software engineering, electrical engineering. When you get to Circuits 2, right here, you've had algebra, that's solving one equation, one unknown, trigonometry, sines and cosines, Calc 1, taking derivatives, Calc 2, integration. What you do in Circuits 2 is kind of pick up where you left off in Circuits 1, but now start adding capacitors. In Circuits 1, you primarily look at resistor circuits, that's steady state. In Circuits 2, you start adding capacitors. Now what capacitors do is they act as integrators. So what I'm going to need to do is set up a differential equation and then solve it. So if you haven't had Calc 1, Calc 2 yet, don't worry. This is ECE 111, the introduction. What we're going to be doing in this lecture is solve the type of problems you set up here. Basically set up the problem, set up your differential equations, then solve using Matlab. And here's what it's going to kind of look like. This is where we're going to get to at the end of the lecture. I've got three coupled first-order differential equations. This is the change in voltage is the function of the voltages in a circuit. Change in voltage 1, change in voltage 2, change in voltage 3. Using numerical methods, I can find out what the voltage is. If I know what the previous voltage is, or voltage was, I know what the change is, I can move forward in time by 10 milliseconds. Repeat 1,000 times, I can show what the voltage is versus time. So this would be for a three-stage RC filter, three coupled differential equations. If I go to 10 coupled first-order differential equations, I get something like this. This would be a 10-stage RC filter. I'm charging at the capacitors and seeing what the voltages are. This is called the heat equation because it satisfies the same differential equation as temperature. I can solve for temperatures. When you take Math 129, linear algebra, they mention eigenvalues, eigenvectors. Very few people know what eigenvalues are. Even fewer know what eigenvectors are. Well, in this lecture, we're actually going to look at what eigenvalues, eigenvectors are. Eigenvalues tell you how it behaves. Eigenvectors tells you what behaves that way. So this is a fast eigenvector. Very quickly, the voltages decay to 0. If I start with a slow eigenvector, that would be this guy. The voltages very slowly decay to 0. So that's where we're heading. How do you solve coupled first-order differential equations using Matlab? And what are eigenvalues? What are eigenvectors? So let's get started. When you get to Circuits 2, you'll be introduced to capacitors. So back in Circuits 1, you talk about resistors. A capacitor is another electrical circuit element. What a capacitor consists of is basically parallel plates. What this does is that stores energy as electric charge. The units of a capacitor are farads. You can calculate the capacitance. That's a constant times the area of the capacitor divided by distance between plates. The bigger the area, the more the capacitance. The smaller the distance between the plates, the bigger the capacitance. The units of capacitance are farads. And to give an idea what 1 farad is, if you have a parallel plate capacitor, just one set of parallel plates that are 1 millimeter apart, you would need an area of 113 million square meters to have a capacitance of 1 farad. And that's pretty big. So most capacitors are actually in microfarads. 1 farad capacitor is actually pretty huge. On a capacitor, this stores charge. That's like static electricity. If you ever went down a slide and then touch your mom's nose and go, zzz, solder, you're acting as a capacitor. You're storing charge. The charge stored on a capacitor is the capacitance value times the voltage. 1 coulomb of charge is 6.2 times 10 to the 18th electrons. If I have coulombs per second, I get current, or amps. So 1 amp is 1 coulomb in 1 second. When I take the derivative of this, I get chain rule. It's the capacitance times change in voltage plus voltage times change in capacitance. So if you have a time-varying capacitor, this term is important. if you have a fixed capacitor, which is mostly what we have, I get the current is C dB dt. Or going the other way around, the voltage is 1 over C times the integral of the current. So capacitors are integrators. If I know the current integrated, I get voltage. So here's a practice problem. Suppose this is the current through a capacitor. What's the voltage? Well, to find that, I just integrate. If I start at a voltage, I need an integration constant. Like suppose I start at 1 volt. If I do nothing, the integral of 0 is 0, so I take the old voltage and I hold it. I then subtract. This has an area of -1. I subtract 1 volt in 1 second, subtract another volt, subtract another volt. If I integrate 0, I get a constant. The voltage stays constant. I now add 3. This has an area of 3, so I go up by 3 volts. This has an area of 2.5, so I go up by 2.5 volts. This has an area of about 0.7. Integral 0 is a constant. This is the voltage versus time. So capacitors are integrators. What capacitors also do is every capacitor stores energy. Every capacitor adds a first-order differential equation to your circuit. Now, going back to the courses you need to graduate, part of the reason you need Calc 1, Calc 2 to get into Circuits 2 is you're solving differential equations. This is the derivative, differentiation. This is integration. Capacitors integrate. So that's kind of why you take the integration before you take Circuits 2, so you kind of understand how you do numerical integration. In hardware, add a capacitor, I'll integrate in hardware. So any circuit with a capacitor is described by differential equations, which is the reason you're taking so much calculus. And calculus will be covering integration and differentiation and how to come up with the closed form solutions. What we'll be doing in this class is using Matlab to solve your differential equations using numerical methods. That's part of the problem, or part of the power of Matlab. Even if you haven't had Calc 1, Calc 2, I can still solve differential equations using Matlab. It's a really powerful tool. So let's kind of see how you do that. Suppose I have a circuit like this. I've got 3 capacitors, meaning this is described by a third-order differential equation, or 3 coupled first-order differential equations. How do I solve? Well, to solve, what I need to do is write the differential equations that describe the circuit. Now, there's a thing called steady state and transient response. Steady state is, if this is a constant voltage, eventually the voltages settle out to some constant value. Find those constants. Well, when you have a constant voltage, the current is C dB dt, the change in voltage. At steady state, the change in voltage is 0, which means the current is 0. If the current is 0, I can ignore these terms. This is a resistor problem. This is what we did last week. If, on the other hand, this is a step input, then I get a transient response. I want to see, how do I charge up capacitor 1? How do I charge up capacitor 2, capacitor 3? That's solving a differential equation. That's what we'll be looking at this week. So assuming these are initially discharged, like this is 0 volts, before times 0, everybody is discharged, everybody's at 0 volts. What happens when this turns on? Well, this is going to start charging up the first capacitor, which then charges up the second capacitor, that then charges up the third capacitor. Let's solve for V1, V2, and V3. Well, there's a couple ways of doing that. I can use Circuit Lab. In Circuit Lab, I make this a step input. That means this is 0 for t less than 0, turns on at t greater than 0. I'll do a transient simulation. What transient does is it'll sit there and plot the voltages, in this case every 3 milliseconds, and show how the voltages are changing. I will tell it I want to look at what the voltages are. The time of the simulation is right here. I'm going to run it for 3 seconds. I make this about 1,000 times smaller. That gives me 1,000 times, or 1,000 points on my plot. 1,000 is a nice number. 1,000 gives you a nice clean plot. If I do 1,000,000 points, it just takes a long time to run. 1,000 is good enough. And then run. So when I run the simulation, Circuit will show you the transient response. So here's the input. There's my step input. That charges up the first capacitor. It then charges up the second capacitor, charges up the third capacitor. Eventually I reach steady state. The steady state solution is what we did last week. Ignoring the capacitors, find the voltages. This week with the capacitors, I can find the transient response. How do I go from the initial point to steady state? So that's one way to solve. Use CircuitLab. And that kind of describes what happened. I just input charges capacitor, the first capacitor, discharges the second, charges the third. Can I solve using Matlab? Well, there's a couple ways of doing that. If I want to solve, what I'm going to be doing is for a capacitor. Each current through the capacitor is C times dB dt. That sets up a differential equation. The differential equations will all come from finding I1, I2, I3. Now from last week, I can find I1, I2, and I3. I1 is the current for this resistor plus current through that resistor plus this current. By conservation of current, current in equals current out. Those three add up to I1. So I1 is V0 minus V1 over 30 plus 0 minus V1 over 150 plus V2 minus V1 over 40. That's I1. I2 is this current plus this current plus that current. Current in equals current out. Current from the left is V1 minus V2 over 40. Current up is 0 minus V2 over 200. Current from the right is V3 minus V2 over 50, and so on. That's the first step. Next, note for capacitors, the current is C dB dt. So there's my differential equation. There's my first coupled differential equation, second, third. So I actually have three coupled first-order differential equations that describes the circuit. So anytime you have capacitors, you're talking differential equations. Again, it kind of sounds intimidating, but it's actually not that bad. With Matlab, the challenge is, can I write the differential equations? Once I can write them, I can solve those differential equations using numerical methods. So now solve and integrate. So this is the voltage V1, V2, V3. To solve in Matlab, what I would do is take your step size, like 10 milliseconds. If I know the voltages, I know how the voltage is changing. Now move forward in time. So what that kind of does is, suppose I have a voltage right here. This is time. I've got this voltage, and there's the slope. That's how fast it's changing. If I move forward 10 milliseconds, the change in voltage is dB dt times dt. That's your dB dt times my step size, 10 milliseconds, gives me how much the voltage changed. That's my new voltage 10 milliseconds later. Repeat. I get a new derivative. Move forward in time 10 milliseconds. Here's the new voltage. Keep going forward in time every 10 milliseconds. Eventually get the voltage versus time. So repeat 1,000 times. And here's what you get. So what that looks like in Matlab. Here's your RC3. I'm going to start out at 0 volts. My input is 10 volts. There's my step size. For 1,000 iterations, or 10 seconds, calculate the change in voltage. Now integrate. The new voltage at 10 milliseconds later is the old voltage plus the slope times the step size. Repeat for V1, V2, V3. And here's what it looks like. My input charges up V1, that then charges up V2, that charges up V3. I record the voltage every 10 milliseconds. After 1,000 iterations, or 10 seconds, I will then plot the time versus voltage. And what I get is the same answer I got in CircuitLab. There's V1, V2, V3. You just solved 3 coupled first-order differential equations using Matlab. Now, one of the great things about Matlab actually does a really good job at the animation. It's not designed for animation, but it works really well with it. The trick with Matlab is you have to add this pause command. After I plot it, I'm going to pause 10 milliseconds, display the data, then repeat. So doing that, you get to see the voltages change versus time. Kind of fun to see. And after 10 seconds, I can then plot all the data. Okay, so that was for a 3-stage RC filter. Now let's show off a little bit. Let's do a 10-stage RC filter. So for a 10-stage RC filter, let's have all the resistors being the same, capacitors. This is actually also modeling the temperature flow. Along like a soldering iron, I've got a long soldering iron. I'm going to treat this like 10 finite elements. Each finite element has thermal capacitance, that's C. I've got thermal resistance between the elements, that's R. And some heat loss, that's this guy. So this is solving for the voltage on a 10-stage RC filter. This is also solving for the voltage, or the temperature, of a soldering iron modeled as 10 finite elements. So due to the symmetry, I don't actually have to write all 10 differential equations. If I write the differential equations for one node, it'll be the same for all the rest, up until the last node. So for example, in this case, I1 is the current from the left, current coming up, current from the right. Current from the left is V0 minus V1 over 1. Current from the right is V2 minus V1 over 1. Current up is 0 minus V1 over 100. Simplifying, plugging in C is 0.01 or 0.1, dividing. Here's the differential equation at node 1. That'll also be the differential equation at node 2, 3, 4, up to 9. Just change the index. The oddball is node number 10. On node number 10, this resistor is missing. So this term goes away. And what I get is this for the 10th node. In Matlab, I can then solve for the voltages. Once I know the voltages, I'm actually going to use an array in this case to save some time. I've got the node voltages, V1 through V10. The differential equation at node 1 is 10V0 minus 20.1 V1 plus 10V2. Index goes up all the way through 9. The 10th node is the oddball. That's a little bit different because there's only one 1 ohm resistor attached to it. Once I know the voltages, I know how the voltage is changing. Move forward in time 10 milliseconds and repeat for 100 seconds. And what I get is this. It's going to show us off better in Matlab. So go to the 10-stage RC filter. I'm going to start out at 0 volts. Let that run. And that charges up V1, it charges V2, charges V3, charges V4, and so on. Let this run for 5 seconds. And after 5 seconds, I save all the voltages. After 5 seconds, I will then plot. Here's the voltage versus time. I've just solved 10 coupled first-order differential equations. This is also the heat equation. If I had a soldering iron, the base temperature was 10 degrees. Here's the temperature as I propagate down the soldering iron. Okay, so that's part of the power of Matlab. I can solve differential equations using Matlab. The challenge is I just have to set up the differential equations, and they're really actually not that bad to set up. Solving by hand is kind of painful. You'll do that when you take Calc 1, Calc 2. In this class, if I could just set up the differential equations in Matlab, I can solve. Now, one kind of other sidelight we're going to talk about are eigenvalues, eigenvectors. Now, eigenvalues and eigenvectors are covered in linear algebra. There is something that very few people understand, and part of the problem they have in linear algebra is they have to make this course generic for all majors. Well, we don't have to do that. This is electrical computer engineering. We can give you a concrete example, an RC circuit, and show you what eigenvalues, eigenvectors are. Part of the reason I'm doing this is so that when you get to linear algebra and you're trying to figure out what the heck are eigenvalues, eigenvectors, kind of refer back to this problem. This is a good way to illustrate what they are. So, a little bit of background. Suppose I have a first-order differential equation, like the change in x, dx dt is minus 3 times x, with some initial condition. When you take Calc 2, you'll assume x of t is in the form of an exponential. When I take the derivative, I get s e to the xt. So plugging into this differential equation, I get the derivative of x, sx, is minus 3 times x. Bring the x left, solve. That tells me that either x of t is 0, that's the trivial solution, or s is minus 3. This is actually the solution that you care about. That means that this differential equation, dx dt is minus 3x, has a natural response of e to the minus 3t. If I plug in my initial condition at t equals 0, e to the 0 is 1, so that's my initial voltage. There's my voltage versus time. That's for a first-order differential equation. This also works with matrices. If x dot equals ax, then my transient response will be my initial condition times e to the at. Now, if A is a square matrix, like a 10 by 10 matrix, it has 10 eigenvalues, 10 eigenvectors. The eigenvalue tells you how it behaves. Something decays as e to the eigenvalue times time. The eigenvector tells you what behaves this way. This is the mode that decays as the first eigenvalue. This is the mode that decays as the second eigenvalue, and so on. So this is probably all confusing for you right now, but hopefully this makes a little bit more sense in a sec. Just remember that eigenvalues tell you how it behaves. Eigenvector tells you what behaves that way. So suppose my initial condition at x equals 0 is an eigenvector, like it's 3 times lambda 1. If that's the case, I know that a1 is 3, everybody else is 0. If my initial condition is an eigenvector, then this mode is excited, everybody else is 0. That's kind of what eigenvectors are. They're telling you the initial condition, which modes are being excited. So let's go back to that 10-stage RC filter. In matrix form, I had B1 dot is minus 20.1 B1, B2 dot is minus 20.1 B2, and so on. This is the matrix form that represents that. This is a 10 by 10 matrix. When you get to Math 129, you'll learn that an n by n matrix has n eigenvalues and eigenvectors. Let's see what those are in Matlab. In Matlab, I can input that 10 by 10 system. Most of the terms are 0, so I'll input that as a 10 by 10 matrix of zeros. The diagonal terms are minus 20.1, off-diagonal terms are 10, and the oddball right here is minus 10.1. I'll just have to input that manually. So there's my 10 by 10 matrix. In Matlab, if I have 10 eigenvalues, I have 10 eigenvectors. Our 10 by 10 matrix has 10 eigenvalues. If I find the eigenvalues of A, that's the Matlab command for eigenvalue, I get 10 answers. What this tells you is I have 10 modes. There's a fast mode, decays as e to the minus 39t, a slow mode, decays as e to the minus 0.3t. That's an eigenvalue, plus there's 8 other modes. If you want to know what behaves that way, that's an eigenvector. Now in Matlab, you actually have to ask for the eigenvector. If we return 2 parameters, I get the eigenvector and the eigenvalue. The reason for that is very few people know what an eigenvalue is. Even fewer know what eigenvectors are. So if you want to know the eigenvector, you've got to work for it. Here's the eigenvectors, here's the eigenvalues. What the eigenvector is telling you is if this is my initial condition, I excited this mode, that mode decays e to the minus 39t. If this is my initial condition, I excited the second mode. That decays as e to the minus 36t, and so on. So here's the fast mode, here's the slow mode, and there's actually 8 other modes. If I make my initial condition the fast mode, that'll decay as e to the minus 39t. So let's see that. Over here, let's make, here's my A matrix, here's my eigenvalues, eigenvectors. Let's make my initial condition the fast eigenvector. I'll make the initial value 0, make the forcing function 0, somewhere, b0, this is my forcing function b0, 0. Let that run. If I do that, let's just do this for 1 second. Here's what happens. Poof. That quickly went away. That decayed as e to the minus 39t. To watch it go slower, let's make this 10 times slower and try it again. Go. The shape is the eigenvector. They go hot, cold, hot, cold, hot, cold, plus, minus, plus, minus, plus, minus. Very quickly, that goes to 0. That's your pass mode. Let's try that again. Here's your pass mode. There's also a slow mode. That is the 10th eigenvector. So let's go over here. The 10th eigenvector decays as e to the minus 0.3t. So there's my shape. That's the eigenvector. The amplitude is decaying really, really slow. E to the minus 0.3t. And let's speed that up a little bit. Let's make the step size 10 times bigger. And let's run it for 1 second. There's my slow mode. Again, the shape is the eigenvector. The amplitude is the eigenvalue. And there's actually 10 total modes. So if I look at the second mode, that was pretty quick. Here's the second eigenvector. Note the shape stays the same. That's the eigenvector. The amplitude is the eigenvalue. Let's go to the third eigenvector. Decays a little bit slower. Fourth eigenvector. Again, the shape stays the same. The shape is the eigenvector. The amplitude is the eigenvalue, and so on. Okay, so here's a question for you. Suppose I make the initial condition random. What's going to happen? Well, let's try it. Here's my random initial condition. And let's run it for 1 second. If I give it a random initial condition, I've excited all 10 eigenvectors. The pass modes decay quickly, leaving the slow mode. And right here you see a shape. That was the slow eigenvector. So very quickly it reverts to the slow eigenvector. I'm looking at an eigenvector right here. And that's not just chance. Anytime I run this, I get a different response. It's random. But at a random input, I excite all the eigenvectors. Fast modes decay quickly, leaving you with a slow mode. So here's a practice problem for you. Write the differential equations for this circuit. Let you pause the video for a second, try to write these. And when you take circuits 2, what the instructors try to do is try to make sure that you've learned the techniques, not memorization. So here, this is the same problem we had before. I just add that 40 ohm resistor. Probably a circuit you've never seen before. If you memorize your way through, you're going to get stuck. If you're learning the concepts, however, it's not an issue. So I1 is just going to be the sum of the currents. It's first current, second current, third current, fourth currents. Those all add up to I1. I1 is C dB dt. So 0.1, spell 0.1 correctly, 0.1 times the derivative B1. This means derivative. That's equal to the current from the left, B0 minus B1 over 10. Current up, 0 minus B1 over 300. Current from the right, B2 minus B1 over 20. Plus the current from the right, B3 minus B1 over 40. If you learn the techniques, the currents have to add up. That resistor is not a big deal. If you're memorizing the circuits, you got a problem. Likewise at node 2, I'll have 0.2 times the derivative, dB2 dt is equal to the current from the left, up, and right, likewise at node 3. Once you get the differential equations, solving in Matlab is actually pretty straightforward. So kind of in summary, capacitors are integrators. What capacitors do is each capacitor adds an integrator or a first order differential equation to your circuit. The voltage on a capacitor is just the integral of current. If you want to describe a circuit with capacitors, you need to use differential equations, hence the reason you're taking so much calculus. Once those differential equations are found, the voltages can be found by using numerical integration. Also, when you set this up in matrix form, you're going to have an n by n matrix. An n by n matrix has eigenvalues, eigenvectors, something you'll cover when you get to Math 129. Again, that confuses everyone. Just remember that eigenvalues tell you how a system behaves. A slow eigenvalue, like e to the minus 0.3t, decays slowly. A fast eigenvalue, e to the minus 39t, decays quickly. That's eigenvalues. Eigenvectors tell you what behaves that way. Each eigenvalue has an eigenvector. The fast eigenvector decays quickly. The slow eigenvector decays slowly. So that's week number 10 for ECE 111. That should be enough to get you started on the homework for this week. And if you need help on the homework, please refer to Bison Academy and the solutions to the previous homework sets for the previous semesters. The problems change every semester, but it's kind of the same theme. So once you see how it was solved last semester, you should have a pretty good idea how to solve it this semester. That's week 10 for ECE 111.